So our next speaker is Professor Colm-cille Caulfield. He is the head of applied math and theoretical physics at the University of Cambridge and a fellow and college lecturer in math at Churchill College. He's no stranger to the University of Toronto, having done a postdoc here. So thank you very much, Colm, for agreeing to talk.
I'm worried. What can you see? Can you see a single slide?
Yeah, so we've got your presenter view. So I think sharing the other screen. Or...
I need to share the other screen. Give me a second. I'll stop that. So let me try again. How about that?
Yeah, so that's perfect. We've got you.
That's better. Okay, well, thank you very much for inviting me. As Rohan said, my name's Colm-cille Caulfield. I'm the head of the Department of Applied Maths and Theoretical Physics here at the University of Cambridge. And I'm also, at the moment, the co-lead of the Cambridge Centre for Data-Driven Discovery, which is one of our interdisciplinary research centres. And though I don't really work in the area of reproducibility, I was invited to give this talk, and I thought it would be a great opportunity for me to do three things. One is to highlight, just to give you a snapshot of the sort of things that we're thinking about in Cambridge in this area, though my colleague Stephen Eglin will give a talk today as well, where he's a specialist in this area. And then also, to talk about very briefly two of my colleagues' work, which has some resonance with what Ben has just been talking about the importance of reproducibility and more generally sort of transparency if you actually want to make some impact. And then just in the last few minutes, I'd like to talk a bit about some of my own research to do with trying to understand climate science, where I'll try and highlight to you just how important reproducibility and an honest discussion of the uncertainty in our models at the moment is critical to us understanding our changing climate. So there's a picture of the Centre for Mathematical Sciences where we're based, and just a little snapshot of what the two departments that we have here, Applied Maths and Theoretical Physics and Pure Maths and Mathematical Statistics. There's about 120 academics and maybe 500 other researchers, either postdoctoral or PhD students. And really the reason I'm just talking about this is to show how over the last few years, last 10 years, we've really very strongly pivoted towards mathematics of information and data science. We're now the host of the Cambridge Centre for Data-Driven Discovery, which I've already mentioned, and I'll come back to that. Also the Cambridge Mathematics of Information in Healthcare Hub, the Cambridge Centre for AI and Medicine, which is supported by AstraZeneca and GSK. And then also very recently, the Institute of Computing for Climate, which is supported by Schmidt Futures. And that very much is designed to try and apply many of the principles that Ben was talking to about open access to codes, open access to data, all the culture of reproducibility and openness to the modeling of our changing climate system. So, like I said, over the next 20 minutes or so, I'll try and give you a flavor of some of these various types of things and show to you how important having an attitude of being open and your science being reproducible is extremely important if you actually, it was almost as if I'd set Ben up with a question, if you actually want your research to have a real world impact. And that's a thing that we've been very much focused on, trying to address problems for society and communicate with people in society. And if you're actually giving advice to the healthcare profession, if you're giving advice to policy makers about how the climate is changing or not, it is critical that you are open in the codes that you use, in the approaches that you use, and the use that you put to data, matter for multiple reasons, of course. One of those reasons is that, it is your responsibility to society to give as open advice and just the scientific facts. But also, and I think Ben was alluding to it as well in terms of this aspect of collaboration, it's incredibly helpful if somebody else can look at your code and somebody else can look at your work, because they may find some insidious bug or some insidious assumption, or they might have a better idea of how to move things on. And that's very important for us to be open in that way to get those things going forwards. So like I said, we have all this different activity here that's become in the broad area of data science. And now I'm just going to talk about a couple of examples from some of these two other centers before I start talking about a bit about how reproducibility is important in my own research. So, like I said, we have this Cambridge Centre for Data-Driven Discovery. The whole idea is that it brings people from across the university and also from industry together into how you use data science in a broad range of areas. And really, the overarching themes that we've identified all certainly resonate with, data management and processing. That's Ben was alluding to that, about how important that is in terms of that being open and reproducible and in a format that you can use. How important it is ethically to understand the ethical dimension and the policy dimension when you're dealing with applications of data science and AI. But also, of course, we're inevitably kind of mathematicians, and we want, or at least some of us are mathematicians, and we want to understand the theoretical foundations of how things are working, so that how the calculations are actually working, so that we can understand how to solve problems that are actually fundamentally of interest. And indeed, we have a key partnership with Aviva, and hopefully a strengthening partnership and friendship with the University of Toronto, in particular DSI, going forwards, because that's it seems there's great complementary interests. But like I said, I'm one of the co-directors at the moment, but one of the original co-directors of it is my colleague Carola Bibiane Schoenlieb, and she is a world-class researcher in applied mathematics in general, but particularly she does some beautiful work in the mathematics of imaging. And a big focus of her at the moment is this Cambridge Mathematics of Information in Healthcare Hub. And I'd just like to highlight this piece of work that they did associated with COVID-19, and also that was recently published in Nature Machine Intelligence, as an example of how important it is to understand the ethical dimension, and also broadly the sort of idea of transparency in your research if you actually want to make a real world impact. So the fundamental idea they had was, would it be possible to develop using convolutional neural networks to be able to, from CT scans, identify the particular diseases that somebody whose scan was taken might be suffering? Were they badly suffering from COVID-19? Was it a bacterial infection, some other viral infection causing the observed pneumonia, or were they indeed healthy? And they were thinking, and it's a beautiful sort of issue, right? How do you aggregate and information from multiple hospitals to improve your diagnostic tools and exploit all the amount of data you have from many different possible data streams, while still ensuring the privacy of both of the individual hospitals, the individual patients, and the situation in the hospitals across international boundaries or across systems, just have a mechanism by which it's possible to share all that information and yet then be able to test it reasonably. Another hospital might produce a similar, run their same piece of code and see if they get a similar set of parameters to their federated models. It's a really beautiful piece of work, and it demonstrated to me just how important it is to always have in the forefront of your mind the ethical dimensions of using data science techniques, and also how important it is that the calculations and the algorithms that you have can be openly tested. So they produce the federated model, but then another hospital could access the same system, the same system, and see if they indeed got similar results or different results, or how it improved the results. So I thought that was a beautiful example of the sort of thing that you can do. Another example that you can do comes out of Mihaela van der Schaar's group in the Cambridge. She's the director of the Cambridge Centre for AI in Medicine, which is a partnership with AstraZeneca and GSK, and is based around this sort of sweet spot Venn diagram idea of how can you combine expertise in science, expertise in medicine, expertise in machine learning to actually advance our understanding of medicine and biomedical science, as well, drug trials, and so, as well as medicine and healthcare. And similarly, they nimbly responded to the COVID crisis by thinking, how can machine learning improve the capacity planning and analysis system, the CPAS, of hospitals? How could they deal with the surges of demands that they could experience as different variants pass through the system? And so the real critical aspect here is, how can you communicate transparently to extremely stressed and harried healthcare professionals who, while still managing to use the data in a rational way? And so the beautiful aspects that resonates with this workshop about the reproducibility is that they built in, not only they had this information flow, not only having a trend using historical information about, it's busier in the winter for respiratory diseases, and then come up with some idea of what the admissions that might be expected at a given time as we saw things going on, and then also have information for different distributions of patients to understand what risks they might experience to be admitted to the hospital. But that's all, I don't want to say that's a beautiful piece of work, but that's all classical, that makes sense to me about the way you might try and do machine learning to give something predictive to healthcare professionals. But what the extra beautiful bit they added in was that they allowed a scenario planning component within their tool. They allowed the hospitals to say, well, if many of our staff are off sick, or if it turned out to be more infectious in this fashion, or the onset of the new variant, that they could manage to run all these sort of extra simulations within that an interface was designed for the healthcare professionals to actually be able to access this model in a sensible fashion, to be able to test the predictions of what was going on. And I thought that was a really beautiful aspect that had, once again, at its core, this fundamental idea of having openness to the nitty-gritty of how your code works, and openness of how your data flows were designed. And so that brings me on to my own particular area of interest, which, as I said, we've recently got this new institute supported by Schmidt Futures, the foundation of Eric and Wendy Schmidt. And their concept really resonates very much with what the university's been involved in, trying to this climate change initiative, which we call Cambridge Zero, led by Emily Shuckburgh, Professor Emily Shuckburgh there, who's a professor in the computer science department here in Cambridge. And there she is at COP26, trying to actually engage with the policymakers and explaining the different sort of science. And really, this institute is saying, okay, we really want to understand how our climate is changing, but it's critical that that the software and the models that we use are transparent, are open, and are sustainable, in the sense that other people can use our codes, understand how the codes are designed. Ben alluded to this as well, right? If you have open, if your source is completely open, that gives you a great imperative to make sure that the code is very well constructed. So we're trying to use the very best principles in software engineering, working with other science teams across the world as part of this Virtual Earth System Research Institute, to really try and understand how to advance our understanding of our changing climate, starting from the principle that all the codes have to be open, the data used has to be open, and so that the software has to be of the highest quality, so that it's well designed, so that the results of it are reproducible, and there's no hint of any black box associated with it. And that question was very, it's not about getting the next paper, it's all about getting the impact on saying this is actually the most believable set of climate predictions that you could want to have, addressing different issues to do with the climate. So I'm very enthused about it, and it's a very nice idea, because at its bedrock, it has this point: any research that is output has to be open and reproducible, because only then can we gain confidence in what the ultimate predictions are. And so then what I'm going to talk about is about why, particularly in the climate problem, because we have such a complicated climate system, having confidence in our predictions is very, very important. And there is still a very long way to go, I would argue, until we can be sure about the right ways to do uncertainty quantification of the various aspects of some climate models. So here is my favorite video created by Kathleen Doan of Earth and Space Research. This is from ocean currents, constructed using a model that assimilates data, altimetry data from satellites. And you see the rich array of currents that occur in the ocean and the complicated kind of weather that's going on. You can see immediately where the equator is, where the component of the Earth's rotation changes. You see these strong currents along the equator. You can see the Gulf Stream with its beautiful eddies, but you can also see the Agulhas current of South Africa and its beautiful retroflexion, which of course is a signal of the fact that the Antarctic circumpolar current is flying around and bends it back. The Antarctic circumpolar current is going from west to east. Which of course determines how difficult it is to get past Cape Horn, for example, in a sailboat. Okay, so there's this beautiful array of currents in the ocean, and the ocean is a key controller of our changing climate system, and we should be very, very concerned because it is rapidly changing, and the oceans are heating up very markedly. Here's from now 3 years ago from the Guardian newspaper, but you can certainly see this upward trend in the heat content of the oceans, which is going to majorly affect the sort of currents that I was showing there. And a key component in that is this idea that we have in the world's oceans of this conveyor belt, right? So we had these currents. We saw the Gulf Stream going northwards along the east coast of North America. You have, at the moment, deep water formation at Greenland and around Antarctica, because there's still ice there, which causes a return flow. And the amount of transport of heat poleward in the world's oceans is measured in the petawatts, 10 to the 15 watts. It's a gigantic amount of heat, because the heat capacity of water is vastly greater than the heat capacity of air. If you think of the column of the atmosphere above a certain part of surface area of the planet, all the way up to 100 kilometers, where Jeff Bezos defines space to start, and think of the heat capacity of that amount of gas. The amount of heat you need to raise the temperature of that volume of air by 1 degree is the same as you need amount of heat just to raise the temperature of 3.4 meters depth of water, 10 feet. Tiny, tiny amount of the depth of the ocean. So the oceans are great heat reservoirs, and it's critical to understand how heat is transported around in those reservoirs. And a key component of how heat is transported around in those reservoirs is through turbulence in the ocean interior due to breaking waves. And so I'm just holding up as the example, how can you model the turbulence inside the ocean that is causing the closing this system? Because this turbulence is happening on scales of meters or less, or centimeters, and yet it is controlling circulations on the scale of 10,000 kilometers that are changing on timescales of decades. So you can't possibly imagine how to do a simulation. You've got to have a model of it that will be constrained by data. And so the question is, how reproducible is your model going to be constrained by data? And this is part of the reason why things like the projection of how the sea level change, for example, have got such enormously large error bars, because there's a great amount of uncertainty in our models of the global climate system. And so we have to have some mechanism of being able to quantify that, and also some mechanism of being able to justify how uncertain that is through the sort of philosophical principles of having reproducible science, because our predictions, of course, come from large-scale numerical simulations that parameterize all these different physical processes, like the ice sheet, the melting ice sheets, like the clouds, and like this interior wave mixing that I've described in the interior of the ocean. So how can we quantify how significant that mixing is? And there are many, many, many processes bouncing around inside of the oceans to do with tides, to do with currents, to do with forcing by surface storms. And yet we want to understand how turbulence happens in the interior of the ocean. And the classical way that oceanography, one of the ways we parameterize it, is there are surveys of cruises of ocean-going ships, and they measure profiles of the velocities in the ocean and the density stratification in the ocean, and then try and use models to infer how much turbulent mixing is associated with those measurements. And how certain are those measurements? So what we did as one study is we said, okay, we're going to imagine we do a simulation, quite a large simulation of a bit of the ocean. And then we imagine we take profiles like an oceanographer an observational oceanographer through that bit of the ocean, and ask the question, okay, we know how much turbulence is going on in our simulation. How many profiles would we have to take using the oceanographer's models to get a good estimate of the turbulence using the techniques they did? And the results were very, very sobering. You'd have to sit through a graduate course on ocean turbulence to understand, for me to explain all that's going on here. But there are 4 classical models that are used, which are shown in green, blue, magenta, and red. And through our synthetic simulations of dropping multiple profiles like we were an oceanographer, we got a statistical estimate of how close the key mixing parameter was, the key turbulence parameter was, to the real value, which for 3 different simulations is shown with the dashed line. And the key takeaway message is each one of the predictions is enormously uncertain. I mean, enormously uncertain compared to the true value. If you take 5 profiles, for example, here, using the red model, you would have an error estimate. Your error estimates are off the charts. They're 500% plus or minus 500% is your answer. Indeed, you even get the wrong sign. And so what this was is this paper that we published once again about 3 years ago was really trying to say, you have to have so much uncertainty in your estimates of what the ocean mixing is. You have to be very wary about predictions you have based on these sort of parameterizations for how the stratification might change as you change the boundary conditions effectively by melting the ice caps. Now, climate predictions at the moment are very good, I would say, because a lot of them, they're based on assimilating data and kind of the idea of weather forecasts, and indeed ensembles, they do many, many, many calculations. But I'm trying to say that it's sobering to think that if we change the situation greatly by melting the ice caps, we could have a very, very different dynamic in the ocean. So we need to try and understand things better. So what we've done is we've said, can we actually use methods of data science and exploit the uncertainty by using, trying to do a probabilistic assessment, not say the individual measurement we take through our turbulence simulation is a matter of truth, but what we're actually trying to do is trying to sample from a statistical distribution of possible events and identify the distribution from which we're sampling rather than the actual value. And this is a beautiful piece of work by one of my PhD students, Sam Lewin, which was recently in Europe. And really we said, okay, once again, we're going to imagine we're an oceanographer. We're going to, through a numerical simulation, drop a profile, measure a profile, and all we'll do is we'll measure what the oceanographer measures, but we'll use that data not to say it's the truth, but to train a neural network to say what is the most probable distribution of turbulence from which we're taking this sample. And so that's what he did. He would take these patches of the ocean, and he would take take measurements and train his probabilistic neural network from these profiles to try and construct the key parameters, the turbulent dissipation, but also critically uncertainty estimates about how uncertain he was in the profile. And this worked out, doing the classic probabilistic neural network, and it worked really nicely. So we would take the profile, the inferred distribution of the turbulence is the picture in the middle, and the true, i.e. what we got from the simulation, is the picture on the right. And so effectively, the distribution we were identifying of the properties of turbulence from our neural network is the magenta line. The truth from the direct numerical simulation is the black line. And what oceanographers traditionally did, the classic surrogate model is the magenta line. At 4 different time steps, the neural network works really well, but beautifully, it also manages to give us uncertainty estimates. And so, once again, I have given you I'll loop back to what I wanted to say. In Cambridge here, we're doing a lot of stuff in data science. We're trying to have impact with decision makers and policy makers. And the key principle of having reproducible open access to our data allows you to be, and our algorithms, allows you to be honest give honest, unbiased advice that is comprehensible and usable from policymakers, but also can reveal to the community the areas that the academic community, the areas that might need addressing, because rather than saying this is the way you do something, we have a deterministic model with a black box, we do that calculation, we get a prediction, we should much rather be saying, well, no, if you appreciate the areas of uncertainty, you may be able to use the methods of data science, if you keep things open access, to be able to say, well, now you can test for your how uncertain your predictions are, because you should be thinking in this more probabilistic way and understanding the uncertainty in your measurements rather than being certain, rather than religiously state something certain, which may not be the right answer. So thank you very much, everyone, for listening, and I'd be happy to take questions if people would like to ask questions.
Thank you very much, Colm. Really appreciate that. If anyone has any questions, please raise your hand and I'll call on you. My question is, so you're in applied mathematics and theoretical physics, but it feels as though you're drawing a lot on computer science. And so do you work closely with computer scientists, or are you starting to hire them into those departments? How does that sort of relationship work?
That's very good. The boundaries are somewhat artificial. I mean, so yes, we have one of our recent hires was a guy called Hamza Fawzi, who was in computer science. He did his PhD in computer science in MIT. And the boundaries are really quite diffuse. I think Cambridge is an amazing place for multidisciplinarity because of our college system. You kind of encounter people, and I mentioned, Emily Schuckler is a professor in computer science, but she used to be on the faculty of DAMT. And so we're trying to build connections that way, and the boundary between when what might be called computer science somewhere else and what will be called applied maths here is a matter of accident. So quite a few of the people in our department could just as easily be sitting in a computer science department, and certainly several of the people in computer science could be sitting in our department. And so I mentioned the CCA, Mihaela van der Schaar's directing it, but several of the faculty involved in that are faculty in the computer science department as well. So there are a lot of cross connections between different departments. And I kind of like to use the analogy that the departments are a way for students to know where to study. But in terms of the research, there can be such when you go through that front door, the research groups can cut across boundaries. Of course, there's a lot of interconnections, kind of you could tell with different aspects of biology. Indeed, in some light, Stephen Eglin would be a neuroscientist. And then and similarly the physics, of course, where does what we call theoretical physics start and stop compared to what physics does? And indeed, with me, my research interest in oceanography, I have a lot of collaboration also with the people in the Earth Sciences department.
Yeah, it's a problem we're grappling with here in terms of like, how do you structure things? We don't have the strong college system that you have, obviously. So thinking about structures is always difficult. Does anyone have any other questions for Colm? Iman?
Hi, good morning. Thank you for the talk. I'm just wondering if at Cambridge you're aware of any studies on antimicrobial resistance, health security in terms of One Health, the animal-human environment interface. I'm a public health physician working with global health, and my interest is in health security.
The honest answer is I don't know. I don't know. Yes, that isn't my area of expertise, and though we do have quite a indeed, I should have said, Mihaela has a joint appointment with the Department of Public Health. I don't know what's going on. I don't know in detail what research they're doing there. So I'm sorry, I don't know the answer to your question.
No problem. Thank you.
Are there any other questions from folks? I'll just say thanks very much for your talk.
You're very welcome.
Very
interesting.
interesting.
So I'll stop sharing. There we go.